Welcome back to Merrill Math. I'm Mr. Merrill, and today we're going to be talking about explicit and recursive rules for quadratic functions. So for these are a little bit trickier than explicit and recursive for linear functions, like we've talked about before, and exponential functions. And in a later video, we'll get into cubics, and I think that's probably about as far as we need to go. There's kind of a pattern that develops, as we'll see, and you can take that pattern and kind of extend it to functions of higher degrees. But we will talk about quadratics today. So explicit and recursive rules for quadratics. So the first thing we got to talk about is what do we mean by explicit form and what do we mean by recursive form? So what do they look like, respectively? So the standard explicit form is in the form of f of x is ax squared plus bx plus c. So our job is to find out what a, b, and c are when we're finding explicit form. For recursive form, it looks a bit more intimidating, but it's not terrible. It's actually pretty easy to find once you know what you're looking for. So recursive form, as we've seen before, looks a little bit different, and it's got this big curly Q brace thing going on here. It has some weird notation. So f of x is our first output if x is our first input, and that's what our little star here is all about. So f of x sub 0 or x sub null or x sub naught, this is our first output if x is our first input. So x sub 0 is our first input. This notation here, f of x minus 1, means, well, if we're trying to find f of x, let's say f of 3, for instance, we would take f of 3 minus 1, or f of 2. This is the previous output to this one. So for finding this one, we have to take the previous output. And this part, I couldn't find a good way to notate this in a way that made sense. This b and this b are different, so don't confuse those. But a good way to think about this is the last part here is a linear function. And this is found from our difference columns once we get to our tables. So this is a slope of a line, and this is basically a y-intercept, or what we're going to find with respect to what our line is. It's not exactly a y-intercept every single time, depending on where your table starts. But basically this is a linear function, so I've notated it to sort of bring that to mind. So we have what the forms look like. So explicit form, recursive form. So this is the difference between them. But the important thing, all right, let's switch pages here. So the important thing is, when we're dealing with these, is, well, I guess the first question will be, how do we know the function is quadratic? Well, the answer to that is the delta squared, or the delta 2 column, or the second difference column, is constant. So difference, or what do I want to say? Delta, this triangle, is a Greek letter. It's what alpha, beta, gamma, delta, right? Fourth letter. So this is the Greek letter delta, and it means change, typically in mathematics. So that's how we're treating this. So we're thinking about this in terms of change from one output to the next, or from one number to the next. So we'll get into an example here where we're talking about deltas. So for this one, we have an example of a table. So our first question to answer is this quadratic? Well, if it is, then the second difference column will be constant. What I mean by constant is the same output over and over and over again. That's what constant is. So the way that we find these values is to just subtract. When we're talking about difference, that's a subtraction problem. So we're going to take this minus that gives us this. So 134 minus 0, that one's not tough. We're going to take 236 minus 134, and that gives us this. Well, that is 102. Then we're going to take 306 minus 236. That is 70. We're going to take 344 minus 306, and that's going to give us 38. So notice we ran out of stuff, so this last one we're going to leave empty. So that doesn't have anything because we don't have any more outputs, which is fine. We don't need any more. The last column here, same idea. So we're going to take 102 minus 134. Now notice we get a negative number, which is okay. Sometimes we do. That's a negative, what is that, 32. And then we take 70 minus 102. Again, it's a negative. And the difference here is also 32, which is looking good. Here we have 38 minus 70. Well, 38, 48, 58, 68. That's a difference of 32. So we've got, and again, we ran out of numbers. So that one we can't fill in. But we did get a delta 2 column. So this column here is constant. So now we know that what we're dealing with is a quadratic. So that's the first step in these problems, because not everything that they'll throw at you is necessarily quadratic. So sometimes they'll throw different things at you, and you kind of have to figure out what you're working with. So our next step is to find the explicit form. So explicit form is ax squared. So f of x is ax squared plus bx plus c. So there are a few different ways that you can tackle this, finding explicit form from a table. We're going to have to refer to our table here a few times. Now, because we're looking for three things that we don't know, that means we'll need to probably use three pieces of information from the table, or three input-output pairs from the table. So if we start with f of 0, so let's do this. So we're starting with f of 0, so that means when the input is 0, what is the output? So we're looking at that. So our first thing is 0, 0. So the output is 0, and the input, so this x we're replacing with the input, which was 0. So we have a times 0 squared plus b times 0 plus c. So we have a times 0, which is 0. We have b times 0, which is 0, plus c, and that equals 0. This isn't too difficult to figure out what c has to be. So 0 plus what equals 0? Well, we know that c has to be 0. Not too bad. So that's the first bit of information. Now, if we look at f of 1, this is where things get a little more interesting. So f of 1, so if x is 1 and f of 1 here is 134, we have this form, but we're just replacing the output with 134 and the input with what we put in to get that. That was 1 here and here. So 134, make sure everybody can see, is a times 1 squared plus b times 1 plus c, which we know is 0. So I'm just going to leave that out. Okay, so what do we have? We have 134 is, well, a times 1 is a, and b times 1 is b. So now we have this relationship. We don't know what a or b is yet, but we do know that they add together to get 134, which means if I take a and subtract it from both sides, so 134 minus a, well, that's equal to b. So this little bit of information we're going to use here in a second. So the next piece, we have to go back to our table. So we're looking at 2 now. So like I said, we needed to use 3 input-output pairs in order to find this out. First one, we found what c was. This one, we found what b was in terms of a. And in this one, we're going to end up solving for b. And then by extension, we're going to solve for a, knowing what we knew in the last step. So if x is 2, f of x is 236. So we have 236 is, I moved out of the way of the microphone so I could write some stuff, but so 236 is, what do we have here? Ax squared, so a times 2 squared plus b times 2 plus c, which is 0. All right, so we have 236 is 2 squared is 4, so this is 4a plus 2b. So we're just kind of making it look nicer here. Notice from last time we know that b is 134 minus a. So if we replace this in terms of a, then we can solve for a and b. So let's do that. So let's replace this guy. So we've got 236 is 4a plus 2 times b, which is 134 minus a. And then we get some stuff. So let's do some distributive property here. So we got 2 times 134, that is 268, minus 2a, and that is 4a comes along, and that's 236. So now we have this. Okay, so what do we have here? We're going to take 236, we're going to subtract 268. I don't feel like doing that in my head. So let's take a look at that. So 236 minus 268, we get a negative, what is that, 32? Oh, okay. So we've got minus 32. What else? Oh, that is 4a minus 2a, so that is 2a. So this tells us that a is negative 16, and by extension, we can figure out what b is, because we have this from back here. So 134 minus 16, that is what b is, which is all right, I made a sign error. Let's go back. We had, where were we at? We had 236 minus 268. We got negative 32. We subtracted, we got a minus 16. We know that b is 134 minus a. So when we do this, we have to be careful. That's minus negative 16. So it's what it is plus 16. So that gives us plus 16. So that should give us 150 for our b value. So all of this to say, we know what c is. C is 0, so we can kind of ignore it. But our explicit form is going to end up being f of x is ax squared, so negative 16 x squared, plus bx plus c. So plus 150x plus 0, which we don't have to worry about adding that in because it doesn't change anything. So this is our explicit form. Okay, next part. So that one's not so bad. And we have to find the recursive form. So this we are also going to use the table for. Okay. So this is a little bit trickier, but under the same token, it's also a little bit easier. The only thing tricky about this is the notation. So like we had before, f of x is this curly Q guy. What do we have? F of our first output, if, there we go, x is our first input, and then our previous output plus mx previous input plus b. So this is some sort of linear function that we're going to be dealing with here. So what we have to do, this linear function that I'm talking about, is this. So this delta 1 column, we need to create a linear function that defines this. So the good thing is we already have our slope. The slope is just this column. So the minus 32s is the change that's happening in this, and change is your slope. So your m term is actually this. So what we have, if we can think about this as like, you know, y equals mx plus b for a moment, we have y equals negative 32x plus b. Now this b is different than the b that we were dealing with before. So what we need to do is use this input, and we're going to use this for an output to define this linear function. So 0 goes to that, 1 goes to this, 2 goes to that, and so on. So all we need to do is substitute 0 in for x, and then 134 in for y. So we have 134 is negative 32 times 0 plus b. We might be able to see what's happening here. So negative 32 times 0 is 0 plus b. So we have b is 134, and that was pretty easy. So now we can take all of this information and put it together into our recursive form. So there's not much to do here. Sometimes finding the linear function is a little bit harder, but a lot of the information is going to be in the table already. So we're going to use some information from the table. So we need our first input and output, and then we need our linear situation here. Okay, so recursive function. That is f of x is the first output, which was 0, if x is our first input, which is also 0. So when x is 0, the output is 0. What we're doing, in a sense, is instantiating the function here. That's a good word. Okay, so the next bit, we have f of x minus 1. Now that just goes in here, f of x minus 1. So what this is telling you is previous output. So once you find one, you can take that one and find the next one, and then you can take that one and find the next one, and so on and so on. That's what recursion is. So minus. This we have a negative 32, so this is going to be minus 32 times x minus 1. So again, this just goes in there. Now notice this is not f of x minus 1. It's different than this. This and this are different things. This is an output. This is an input. So you have to be careful when you start using this to calculate stuff. I'll show you here an example here in a minute. Plus b. So our b is this 134 here. So plus 134. So let's use this to find some stuff. Hi, me from the future here. As I was editing this video, I noticed that in addition to making a sign error, I also made another mistake. That it happened at the very beginning of the video, and it was a very subtle mistake. But it's important that I correct this, because if I don't, and you go to answer some questions on a quiz or something, your teacher is likely to take some points off if you give the answer that I just got. So we're going to make a slight change to our recursive form. Now, like I said, the notation is the difficult part, and that's what ended up happening here. This was the difficult part. So when we instantiated this, again, that's a great word, we said f of x is the first output if x is the first input. And then we said this thing with the linear stuff and all that. But we need an if statement after this as well. So what we need to add after this is if x is greater than the first input. So if x is greater than x sub 0. So for the question that we had, let me take a look at this. So when we had our recursive form, again, this guy, if x is greater than x sub 0, so that guy. Down here, where are we at? We're right here. This guy. So the table that we had our first output, and then we did some calculation here. This line needs to have this part added to it. If x is greater than the first input, which was 0. So the way that this looks, f of x is this if x is 0. Otherwise, you do some calculation stuff here if x is greater than 0. So if x is 1 or 2 or 3 or 4 or 5. So this is an important part, and this happens in all of them. So every recursive form has to have this little piece at the end, and it's always the same. So this number and this number are always going to be the same, and it's always your first input. Okay, back to the action. So let's say f of 0. Well, we know that if x is 0, f of 0 is 0. Fair enough. F of 1. So that is f of x minus 1. So that is the output here that we just got. So that's 0 minus 32 times the previous input, that's 0, plus 134. So this 0 minus 0 plus 134, that's 134. F of 2 is the previous output, so that's what this says. So the previous output that we got was 134 minus 32 times the previous input, which was 1, plus 134. So we have, what do we have here? So we've got 134 minus 32 times 1 plus 134. What did we get? 236. So that is 236. So we have f of 3. So that is, again, previous output. So we just got 236, so that goes here. Minus 32 times the previous input, which was 2, plus 134. Now notice some things are the same in each of these, and some things are different. These change. So this came from here, this came from there, this came from there. But the minus 32s are always there. This was 0, that came from there, 1 came from there, 2 came from there, and then the 134s are all the same. Okay, so we got to do a little bit of calculating. So 236 minus 32 times 2 plus 134. That is 306. Okay, how did we do? So from our table, move some stuff around here. From our table, we had 0, 0, which we have here. We had 1 and 134. So f of 1 is 134. We got that. We had 2 and 236, and we had that. And then we had 3 and 306, which we had. So we have a recursive function for this. I'm trying to see how long I've been recording. I think it's been a while. So I'm going to call that good for right now. But if there is interest in more examples of explicit and recursive rules for quadratics, let me know in the comments below. If you have any questions, comments, points of clarification, be sure to leave those in the comments below. Otherwise, thanks for watching.